Hey class, Adam Ward here. I wanted to put together this video to walk us through the derivation of the Reynolds transport theorem so that we could be really clear about where this comes from, what good it is, what assumptions we've had to make along the way. And to start this, we're going to think about both a fluid system and a control volume. And so you'll recall the fluid system is the Lagrangian perspective that's about following the particles of water. And the control volume, that's the Eulerian approach, where we focus on a location in space, for example, the tank. And so after some amount of time, perhaps we've let there be a hole in the tank, the fluid system has moved as that fluid starts to empty out, but the control volume would remain the same. And the key difference between the two is that for the control volume to work, you've got to account for the flux out. If you don't, you've simply got mass that is magically disappearing somehow. So to that end, let's first talk about what is flux. And so we can imagine that we're going to analyze a unit area, dA, of that control surface, meaning the boundaries of the control volume, and it has some velocity v coming out, and that velocity is not necessarily perpendicular to the surface, and so we'll define this normal vector n, meaning perpendicular to the surface, or normal to the surface, and an angle theta between the two. If we were to just cut through a slice of the side here, you would see something like this. I just wanted to make sure it was explicitly clear what these vectors were doing. So the normal velocity is the velocity component that's perpendicular to the surface. And so we can use trigonometry to estimate that normal velocity as v cosine theta. Now, in your book, the derivation just assumes that all the velocities will be taken as perpendicular to the control volume. That doesn't necessarily have to be the case, so I'm going to do it this way, but we'll get to the same point at the end. Now, in a unit of time, what volume would have actually left our system? Well, we know that a volume could be defined as the velocity normal to the surface, so that's v cosine theta, times the area multiplied by time. And so the incremental volume dV could be defined as v cosine theta times dA times dt. So I snuck those little d's in there. And there I'm just proving to you the units of meters per second times seconds gives me meters. That times area gives me meters cubed. So we've covered item 1, what is flux. The second piece that we'll need is we're going to start expressing quantities we're interested in per unit mass. And following along with the textbook, we do this by defining capital B as the quantity that we're interested in. This could be mass, it could be temperature, it could be energy, it could be momentum. It's something that you're interested in, and m is the amount of mass. And so lowercase b just describes how much of big B is there per unit mass. So a couple examples. If you're interested in mass, that little b becomes a 1. If you're interested in volume, you end up with 1 over density. If you're interested in momentum, which is mass times, that should be a mass times a velocity, not a volume, you get simply a velocity. So again, those two green V's should be velocities, not volumes as I've drawn them there. My apologies for the slight typo. Now, we've got a quantity per unit mass, we've got flux. Can we define how much actually flows across our surface? Well, let's start from our definition of what B is, that quantity of interest. And we can say, well, the incremental change in B must be the little b, so B per unit mass, multiplied by the incremental mass. And we know mass is density times volume, so we can substitute in for dm instead a density times dV. Now, from the previous slide, I wrote from 2, I think that's where it came from. We defined that incremental volume already as velocity times dt cosine theta times dA. So if you plug that in, you get the following equation that I've just written out here. And I'm going to do one thing which is called the dot product rule. And so you can see that I wrote that a vector dotted with the b vector is the same as a times b times cosine theta. And so I've substituted that in for our velocity and normal vector. And so what I want you to see when you see that dot product is simply meaning that we're taking the velocity perpendicular to the control surface, or the velocity in the normal direction here. So the flux of B across our surface, of capital B, which your book writes as a capital B with a dot over top of it, can be defined as density times lowercase b times that dot product of velocity with the normal vector times the area. So what we've learned here is that the flux of something across our control surface, right, in and out of our control volume, depends on the area, depends on the velocity, and it also depends on the direction of the velocity. Right? So those bottom two bullets meaning it's the perpendicular velocity that we're interested in. Now, we're going to start to pull this together, and we're going to do so by thinking about a control volume and a fluid system at two different times, time 0 and time dt. So we can define the flux out of our system by integrating all of the outward fluxes across the control surface. And similarly, we can define the flux into our system by integrating all of the inward fluxes across the control surface. So those two integrals have cs, comma, out or comma in as their subscripts. And the net flux across our control surface is what went out minus what came in. Or in this case, we can say that that net flux is equal to the integral across the control surface of all densities times little b times those normal velocities dA. Right? So we're integrating all the fluxes, and the plus and minus signs will essentially take care of themselves. Plus is coming in, minus is going out. We can use sort of the conceptual picture I drew above to think about what this is actually going to mean. So at time equals 0, the control volume and the system were coincident with each other. And at dt, we could say, well, what's contained by the system is what was in the volume minus the part that left, which I did in green, plus the part that entered, which I did in purple. And so sort of conceptually, you can see what we're doing is just starting to keep track of how much of quantity B, whatever that is inside of the control volume, how much left, and how much entered. So if we continue bringing this all together, we can say, well, the time rate of change of B in our system, that's what the left-hand side is. And on the right-hand side, I've just taken the numerator there and made it a finite difference. It's the time over that interval dt. And if we sub in our definition from the previous page, this can grow and start to look a little bit uglier. There we go. And so we've got this first term, sort of the one that's got 2 bits in the numerator, keeping track of the change of B inside the control volume, and then you can see inflows and outflows there on the right, with that B1 and B2. And if we simplify this down, we can convince ourselves that the time rate of change of B in our fluid system has to be equal to the time rate of change in the control volume plus the net fluxes of B across that control surface. And so just to spell that out and make it explicitly apparent, that first term is the time rate of change of B in your fluid system. Second term, time rate of change of B inside of the control volume. And then we've got to keep track of that net flux of B across the control surface, right, across the boundaries that define the control volume for us. If you're with me there, let's go one step farther, and we're going to formalize this into what's called Reynolds transport theorem. And it's going to have the exact same 3 terms here. the time rate of change of B in the system on the left-hand side, and underlined in blue, is equal to the time rate of change of B in your control volume, and added to that is the integrated flux across the control surface. The big change that happened between the left column and the right column was that I plugged back in that definition of capital B, right, where B was a capital B and lowercase b are related by mass, and so that's where the density and volume come into play. Okay, so we've gone through a bunch of mathematical manipulations here to try and relate control volumes with fluid systems. And I think it's important to then touch base again on why exactly we're doing this. First and foremost, although it's somewhat intuitive that this might be how it's logical to keep track of things, what we've done here is start with a very simple surface with some arbitrary vector of a velocity moving across it, and we've gotten to the point where we can define fluxes of any quantity that we're interested in. That could be the water itself, or that could be something the water carries, like momentum or energy. We'll use this Reynolds transport theorem, as I've got it written on the right-hand side here, as the basis for deriving conservation of mass, conservation of energy, and conservation of momentum. Importantly, rather than arbitrarily showing these rules and suggesting that they must be true, we've gotten to Reynolds transport theorem, and so this is sort of like a safe stopping point for us. We're going to pause at Reynolds transport theorem, and then we can push forward from here and simplify out the equations to describe conservation of mass, energy, and momentum through the next couple of weeks of class. One of the reasons I think that's so important is that as you go through that simplification, you start to make assumptions, and those assumptions limit the conditions under which anything subsequently can be used. And so by doing it this way, it forces us to see those assumptions, to explicitly make them, and acknowledge what the limitations will be. Okay, class, so that's about 12.5 minutes of going from a starting point to Reynolds transport theorem, but this way you've got it for your own notes, and you can always circle back and listen to me drone on about derivations if you so choose. All right, I hope this finds you well, and I will see you back in the classroom. Thanks, everybody.